Why was the chord upset with the tangent after their race? They came in secant. Now, that might not make a lot of sense because we haven't really talked about these, but these are special lines, segments, and circles. A chord, a secant, and a tangent. So, looking at the picture at right, you can see I have one that's marked a chord, segment AB. And a chord is a segment whose endpoints lie on the circle. So you can see point A, point B. Both of those points are on the circle. A secant is a line. See how this one is just a segment with endpoints, and this one is a line that continues on forever. So a secant is any line that intersects a circle at 2 points. And then finally, a tangent is a line that's in the same plane as the circle and intersects it at only 1 point. So that point is called the point of tangency. Now, there are also pairs of circles that we will learn about. 2 circles are congruent if and only if they have congruent radii. And concentric circles are coplanar, meaning in the same plane with the same center. Concentric. So remember, we've been talking about before, means to share. Centric comes from center, share, center. And then finally, tangent circles are 2 coplanar circles that intersect at exactly 1 point. Not 2, not all of them. So you can, we've got example 1 here, and I want to label each of these pairs of circles. You can see here, they actually, it might look like they're sharing more than one, but they actually only share 1 point. And they do have different centers. Tangent circles will never have the same center because then if they do, they'd actually have to be the same size. So that is a tangent pair of circles right here. This is another example of a tangent pair of circles. And then these 2 circles share the same center. Notice that they don't intersect at all. And those are concentric. Now, there's some special theorems about tangent segments and lines. If a line is tangent to a circle where it passes through only 1 point, then it is perpendicular. Do you see the little right angle drawn in here? To the radius drawn to the point of tangency. So this radius is connecting to that point of tangency, and it automatically makes a right angle with this tangent line. Now, if I know a line is perpendicular to the radius of a circle and at a point on the circle, then I can also say that the line is tangent to the circle. This is just the converse of the first theorem. Now, here's an interesting thing. If 2 segments are tangent to the circle from the same point, from the same external point, I should say, see external point A right here, then the segments are congruent. And hold on a second. So what that means is that these 2 segments over here, this one and that one, VA, is congruent to AC. And that would be good to add to your notes. So those 2 segments will be congruent. See how we have tangent here, intersects at 1 point, tangent there, intersects at 1 point. There's the external point outside of the circle. So let's take a look at example 2. We're going to use the 2 theorems we just did. The last one we did says that, see, I have an external point, and these 2 are tangent. So I know that this segment is congruent to that segment. Since 2 things are congruent, that means their values are equal. So I can set up an equation saying 4x minus 1 equals 2x plus 9. Then I can go ahead and solve. I have more x's on the left, less x's on the right, so I'm going to subtract 2 x's from both sides. That leaves me with 2x minus 1 equals 9, and I will add 1 to both sides, and I get 2x equals 10, or x is 5. Now, they want to find the length of each segment, so it's not really here that they want x. They want to know what is kj and what is lj. They're both going to be the same answer because they're congruent. So kj, I take this 5 and I put it in for x, so it's 4 times 5 minus 1. That's 20 minus 1, or 19. Lj will also be 19. For the next part of this example, this is another problem, 6y minus 2 and 30y minus 2. Well, how can I tell that these two segments count for that last theorem? Well, the cool thing is that these two segments are tangent to the same circle from the same external point, so they have to be congruent. And this segment is tangent to the same circle from J as well, so that means since they're tangent from the same point, they have to be congruent. So now I can say that 30 minus 2y is the same as 6y minus 2. If two things are congruent, their values are equal, and I can set them equal to set up an equation. So I have 6y minus 2 equals 30 minus 2y. I have a lot more y's on the left side, not so many on the right, so I'm going to undo the minus 2y on the right by adding 2y to both sides, and I get 8y minus 2 equals 30. Then I need to add 2 to both sides, which tells me 8y equals 32, and you should be able to pretty easily figure out this part, y is 4. They didn't ask me for y, they asked me for the segments. So I'm going to take kj and put in 4 in for the y right here. And 6 times 4 minus 2, 6 times 4 is 24, minus 2 is 22. And that is your answer. In example 3, I want to tell whether each statement is sometimes, always, or never true. Two circles with the same center are congruent. So if they have the same center, that means, let's say I have a point here, right? It's my center. There's my center. And pretend I can draw a circle. Then I could have a really bad circle there and another bad circle there. And those are not necessarily congruent, but they do share the same center. If I had the circles that were the same size and shared the same center, I'll pretend the center's there, then that would be the case. So I would say that this is sometimes true, but not always true. A tangent to a circle intersects the circle at 2 points. Well, the definition is 1 point, not 2 points. So this is never true. Tangent circles have the same center. Well, there were only 2 ways we saw tangent circles. One was when they were kind of touching on the edge like that. Definitely not the same center. And then also when we saw them kind of nested, kind of sharing a point right here. A tangent circle can only have 1 point in common. If it had the same center and they had at least 1 point in common, that would make them the same circle like that. So that would not be tangent. So tangent circles never ever have the same center. A tangent to a circle will form a right angle with a radius that is drawn to the point of tangency. So let's pretend I have a tangent in my very sloppy circle, and there's my center. Technically, this is part of the definition of tangent. It forms a right angle with the radius. And so I would say that's always true. A chord of a circle is a diameter. A chord of a circle is a diameter. A chord is just any 2 points on the circle, right, that I connect with a line. It doesn't always have to go through the center. It sometimes can. So I would say that this is sometimes true. A chord of a circle could be a diameter, but it's not always a diameter.